Hi, my name is Uchimado Abuchi Daniel, and this is my enterprise knowledge retrieval and synthesis platform. So, this is a full stack AI system that I built from scratch to solve real problem that large organizations face every day. The problem is that all these organizations they have a lot of internal documents that they use, like policies, research, contracts, and technical manuals, like all of that. And all of these documents are scattered across several places. Some are scattered in the file server, some are in the email, some are in the knowledge bases, and all of that. So the people working in organizations, the employees, spend a lot of time going through all of these documents to get a specific information, and it becomes very very stressful, and even critical knowledge can be siloed. So what my platform is doing is when you upload a document, let's say PDF, Word, or text, the system would process it, understand the content, and then allow you to be able to ask questions about the document. So once you ask any question, it gives you an accurate answer within minutes. So this is not just anyhow project. This is a project that can be used by big companies that have like a lot of documents, large documents, because it's not it is not an let me say an LLM API call. Like it's not a wrapper that you put ChatGPT and you just be getting we are getting content from ChatGPT. It's not an API call. I made use of end-to-end system with proper rack pipeline, hybrid search, MLOps infrastructure, and production monitoring. So let me just show you how this project works. So when you click on the drag and drop files here, you are taken to. So I want to open a project. No, not a project, but let's say I want to open a document. So now this document is a document that contains the history of football. So let me open the content of the document. So this is the content of the document. So this is what is inside the document, and the history of football. So we can look at all the informations here, and we are going to be uploading this PDF, and we'll be asking questions from this PDF. So let's go back to where we were before. So now I've uploaded the document. Now I want to ask a question. So now let's look at the document. So here we say Kuju football. One of the oldest documented ball games resembling football was Kuju, played in China. So I'm going to be copying this text. I'm going to be copying this text, copy, and then I'll be pasting it here. So we want to ask questions. So yeah, one of the oldest documented ball games resembling football. So I'll say, what was what was one of the oldest documented ball games resembling football in ancient China? Ancient China. So once we impute that, so we want to query the system to like for this information. So the response we are expecting is Kuju, for it to tell us that it was Kuju. So let's click on search. So it is searching the document. So what is happening in the background? So that is where we go to the infrastructure. So I want to explain what's happening in the background. So why it is searching for the document. Let me explain what's happening in the background. So on your screen here, you can see the pipeline overview. So once the user mixes of the interface, which is Next.js with REST API clients, then it goes to the Fast API backend. So these are the components in the Fast API backend. and then it goes to the RAG chain. So I am using Olama, or let me say Llama 3.2. So these are the components under the RAG chain. Then it now goes to the retrieval pipeline. It goes to the retrieval pipeline, and then from here it goes to the data storage layer, which I'm making use of ComaDB and PostgreSQL, and then MLOps and monitoring. So these are the components. So um so this is the whole architecture. This is how the architecture is. So let me explain each of the architecture. Let me explain each of them. So finally, the user layer, interface layer is what the user interacts with. That is this what you can see in the screen. Now, from the first API backend. Now, fast API. This is Python's highest performance async web framework. So this application uses a lifespan context manager for proper startup and shutdown at startup. So it performs all the heavy services in the background thread. That is the embedding model, the vector database, and the LLM client. So whenever you impute a request, it doesn't it your request goes fast. It is not delayed by model loading and all of that. So the API, it follows RESTful design with versioned endpoints. So that's for the document uploads, the query, and the health check, all with pedantic schema validations. So that is what is going on in the fast API backend side. So when you come to the RAG chain, like let me explain the pipeline. Is of the system retriever. So it does is um it does um semantic search. So just is that uses sentence transformer. So it uses a sentence transformer mini LM model to generate 384 dimensional embeddings stored in ChromaDB, a persistent vector database. And not just only semantic search that the RAG chain is doing, it also does a keyword search which uses TF-IDF style term overlap with exact phrase boosting. So when you merge these two together, you are making use of, yeah, you are saying reciprocal rank fusion with k is equals to 60. So this is the same algorithm that is used in production search engines. Like most of these search engines, this is what they use. It is mathematically elegant. Each result gets a score of 1 all over into bracket rank plus k, weighted by an alpha parameter that controls the semantic versus keyword balance. So that is what is going on in the RAG chain. So once it does all of that, let's go to the retrieval pipeline. So the vector store supports multiple backends. ChromaDB for local development, Pine, Pinecone for cloud production, and in-memory fallback. This abstraction means I can swap the storage layer without touching any business logic. ChromaDB uses a persistent client, so vector survive server restarts. So the LLM integration. The LLM integration. So um, the LLM integration uses a priority chain. It tries Olama first for local free private inference, and then OpenAI if API keys are available. Then falls back to return raw document excerpts. This graceful degradation means the system works in any environment. Critically, the Olama core runs in a ASIC thread. This is a non-obvious but important details. So Olama's Python client is synchronous, and if you call it directly as an async handler, it blocks the entire event loop by uploading it to a thread. The server can still respond to health check and other requests while the LLM is generating. So so that is just part of the explanation for the retrieval pipeline. So then to the um data storage layer, that's part of what I explained. And yeah, so this is basically the way the system operates. This is the way the system operates. So this is the pipeline. So for further information, you can see the backend. So this is the architecture using backend, fast API, RESTful API design, lifespan context. Then go to the rack pipeline. So this is the content of the rack pipeline. So this is how the pipeline was. I wish this is what I explained earlier. So you make your semantic search, you make your keyword search. When you combine both of them, when it's combined both of them, you merge it using reciprocal rank fusion, and then the llama 3.2 via llama runs on the device, and it doesn't if um so it runs on the device. But then if OpenAI is if you have your open API key, you can still use it. And then for the embedding and the vector store, images of ComaDB, that's the persistent clients that supports metadata filtering for scoped queries. And then Pinecone, I explained that earlier. Then the sentence transformer. So this is what does the document in the JSON. So I'm making use of PyMood PDF. So that's what supports the PDF uploading, and then then it makes use of semantic chunking. So it chunks the results. So and then you go to production engineering. So this is how this is how I'm able to apply MLOps to the platform, and then to Docker and to the rest. So let's check the results. I think this. Okay. So this was the result it gave. So in the question we asked there, we asked the one of the that's what one of the older documents ball games resembling football was that. So this is the answer, Kuju. So let's see what it did. So it went through the entire document. He went through the entire document, and he says, according to source one, this and source two, this is one of the oldest documents ball games resembling football played in ancient China was Kuju. You can see the answer there. And then he also brought the source three history of football. So suppose the information is stating that Chinese played a game called Kuju during the Disney. So he said in all three sources, Kuju is mentioned as one of them. So he gave the answers, and you can see we ranked the response time. You can see the sources, how it's able to do the semantic chunking and all of that, and it gave an overall confidence. So after everything, it gives you an overall confidence. So this will tell you how confident it is about the results. So this is how the knowledge platform works. This is how the knowledge platform works. So if you um if you want to check out the project, you can check my GitHub. You can check my GitHub for more information about this project. So thank you.